Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the fundamentals of probability theory and statistical inference, which are possibly going to be useful in data science. So you can recall that in the last lecture we had understood the geometric distribution. Now the next question is how you can compute different types of probabilities, how you can compute the quantiles, how you can compute the CDF, how you can generate the random numbers from the geometric distribution in the R software. That is the question which we are going to handle in this lecture. So now I am sure that you will be very comfortable with this type of lecture, because the things are going to be on the similar lines what we have done in the case of discrete uniform, binomial, Poisson, etc. But here in this lecture there is going to be one difference. The difference is when you took or when you consider the binomial or Poisson distribution, you had the parameters say n and p in the binomial and lambda in the Poisson distribution, and you simply use n, p, lambda as such. But when you are trying to use this geometric distribution in R, so one of the value which we have used in defining the probability mass function k, the use of k is going to be a little bit different than in the theory. So that is why you have to be very careful. Also I will try to make it clear here, but the reason I told you that you should not be overconfident. So let us try to begin our lecture. So now geometric distribution is defined like as follows. A discrete random variable x is said to follow a geometric distribution with parameter p if its probability mass function is given by probability of x equal to k. Please make a note here, which is equal to here probability p into 1 minus p raised to the power of here k minus 1, and k is starting from 1. Right. This is what we have considered in the theory, and in R you will see, means I will try to show you, this k starts from here 0, 1, 2, 3 and so on. So that is why whatever you are using here as say k in our notations, this is going to be k minus 1 in the notations of R software. If you just keep this thing in mind, there is no problem, right. And the mean and variance that you had already reported, they are 1 upon p as the mean, and the variance is 1 upon p into 1 upon p minus 1. Right. Now let us try to understand what are the commands which are going to give you the different type of density, CDF, quantile, etc. in the geometric distribution. So DGEOM, D means density and GEOM means geometric. This commands gives the density that you know, that is the probability. PGEOM, this gives the CDF. QGEOM, this gives us the quantile function, and RGEOM, this generates the random numbers. Right. Definitely if you try to use some invalid prop, that will result in a value NAN by the warning. So now let us try to first understand, before we try to understand the parameters inside the parenthesis, that there is a slight difference in the definition of geometric distribution in R in comparison to what we have done. In R, this k is the number of failures before the first success. This means we need to specify k minus 1 instead of k of our notation in the functions like d, g, e, o, m, right. So, in the case of geometric distribution in the R software, it is defined as, say, the function p r o b that will be used for p, but that will defined in the following way, that p x equal to p into 1 minus p raised to the power of here x, where x goes from 0, 1, 2 and so on. That is exactly what I told you in the earlier. What we had considered, it is something like p into 1 minus p raised to the power of x minus n. So, we have considered. So, be very careful. Right. So, now the values that you have to give inside the parenthesis, they will be like as here, say x and q, they are the vector of quantiles, p is the vector of probabilities, n is the number of observation, prob is the probability of success in each trial, and lower tail, you know that this is a logical variable, it takes value true or false, and if that is true, you are going to compute a PDF like probability x less than equal to x, and if you try to take lower dot tail equal to false, then it will compute probability x greater than x, right. So, let us try to first understand the application of these things, and then I will try to introduce how are you going to use this values inside the parentheses in different commands. Intentionally, if you try to see here, I have not written that how you have to give the d, g, e, o, m inside something like this, because there was a confusion. So, that is why I have postponed it to the example from where you are going to use it. Okay. So, now as usual, what we have done earlier, we simply try to plot the probabilities, and in order to plot it, we are going to take the value of say k starting from 0 to 100, but you can see here that in this case your x will be actually k minus 1, right. So, but according to the definition what we have learned, it should have been k, but it does not make any difference. So, I am trying to take here the value of k, and then we are trying to choose here prob equal to 0.67, who can take anything, and then we are trying to compute the different probabilities, and we are trying to plot the probabilities with respect to the value of x, right, and the title here will be geometry probability mass function and so on, right. So, if you try to see here, this plot will come like this, that initially the probabilities are here like this, but after some time they will become almost parallel to the x axis close to 0, right. So, now what we do, that we try to consider here the same example that we considered in the last lecture, and we try to compute those probabilities using the R software. So, in that example we had considered that there is an urn which has n white and m black balls, and the balls are randomly selected one at a time until a black one is obtained. And if we assume that each selected ball is replaced before the next one is drawn, then we already had found the probability that there are exactly n draws needed. So, that was probability x equal to n, that was obtained here like this, and at least k draws are needed, that was probability x less than equal to k, which was here obtained here like this, where this p was m upon m plus n. So, now we try to choose here the two values of m and n as capital N is equal to 5 and capital M is equal to 10. So, this p probability comes out to be close to 0.67, and now we try to compute these probabilities using the R software. So, suppose we want to find the probability of exactly n equal to 4 draws are needed, and for that I would like to use the command in the R software. So, basically we want to compute probability that x equal to 4. So, now you can see here you are trying to use here the command d, g, e, o, m to compute the density, but now for the x you are not giving here as 4, but you are trying to give here 4 minus 1, this is k minus 1, and this is your here k. This is what you have to keep in mind, and after that you have to simply write the value of probability as PROB equal to 0.67, which is the parameter of the geometric distribution. And if you try to compute it, it will come out to be like this. And in case if you try to compute the same probability manually also using this expression, you can see here that both these expressions are going to give you the same outcome as shown on this screenshot. You can see here this and here this. Okay, so now we try to compute the CDF. So for that we have the command pgeom q, and then you have to give here the probability, and you have an option to give lower dot tail equal to true or false, right, just like as we have used earlier. So this will give you the CDF fq equal to probability x less than equal to q at any point q. So when you are trying to prescribe this command, then you have to be careful when you are trying to choose here the value of q, right. So that is again going to be something like the k minus 1 type of issue. So suppose we want to find out the probability of at least 6 draws are needed with p is equal to 0.67, then that means we want probability that x less than equal to 6, but we are trying to specify this 6 as in the R software as 6 minus 1. So that means we have to write probability that x less than equal to 6 minus 1, which is equal to 1 minus f of 6 minus 1, and using the command here 1 minus p geom with q equal to 5 and prob equal to 0.67, we can compute this value. Now, and in case if you do not want to use this command of 1 minus f, then you can use here lower dot tail is equal to false, and then you can write down the command as a pgeom q is equal to 6 minus 1 and prob is equal to 0.67, and it is going to give you the same outcome like this one. So, right, that is up to you, whatever you want to use. Right. Now, we try to find out one more probability, that we find the probability of at most 3 draws. So, then in that case you essentially need here probability x less than equal to 3, which is equal to simply here f3, and now you know how you have to give. Instead of writing f3, you have to actually write here say 3 minus 1 in place of 3. So, that will become here pgeom, and this will become here 3 minus 1 and prob is equal to 0.67, and this probability you can obtain from the R software here like this 0.96 and so on. Or means equivalently, if you want to do it here using the lower dot tail equal to true option, you will get the same thing here, and this is here the screenshot. So, you can see here whether you use lower dot tail is equal to true or not, that is not really going to make any difference. This is the default value. Now, similarly, if you want to compute the quantiles, so for that you have to use the command here qgeom and then here p, then probability, and lower dot tail remains the same as we have used earlier. And suppose we want to determine the 80% quantile. So, this is the value q which is going to describe that probability x less than equal to q is greater than or equal to 0.8. So, this can be obtained by the command qgeom p is equal to 0.8 and prob equal to 0.67. So, you can see here how are we going to do it here. So, you write this thing and then you will get here the value here 1, or equivalently if you want to use the option here lower dot tail equal to true, even then you will get here the same value. This is the screenshot, right. And then you can see here that you are getting here the value 1 because geometric is a discrete distribution. And similarly, if you want to generate some random numbers from geometric distribution, that is very straightforward. So, if you want to generate say a small number of observation from the geometric probability mass function, then the command here is rgeom, and you have to write inside the parenthesis the number of observation n and the prob, which is the probability, right. So, suppose if you want to generate 5 random numbers from a geometric distribution with p equal to 0.67, so that can be simply obtained by rgeom and n is equal to 5 and prob is equal to 0.67, and it will give you here such 5 values. And if you try to repeat it, this will give you here say once again means some other values which are 5, and they will resemble as if they are drawn from this geometric probability distribution where the p is equal to 0.67. Right. Now, in case if you want to do a sort of simulation for the geometric distribution that we have done earlier in binomial and Poisson distribution also. So, I will explain you, but I will request you to do it yourself. At least now you have to develop a sort of confidence that what you are going to observe. Well, I can explain you the outcome, but then you have to see whether this is matching with this outcome or not. So, suppose you know that in this case p is equal to 0.67 and expected value of x, that is mean, is 1 upon p, which is 1.5, and variance of x can be computed as 0.75. Now, you try to generate, say, a number of observations from this distribution with prob equal to 0.67 and try to find out their mean and variance, and try to compare that what happens to the values of mean and variance when you are trying to estimate them on the basis of a random sample, where when the true values are like 1.5 and 0.75. The outcome that you will see that as you try to increase the value of here n, say from 10 to 100 to 1000 to 10,000, the value of mean and variance will be approaching towards the true value. Right. So, okay. So, now we stop in this lecture, and now I am sure that this type of lecture will appear to be very easy to you, because I am trying to show you the same thing what I have shown you earlier, only the commands are changing, and you can see one thing, that the commands are not difficult to remember. R, Q, P, etc. they are, or D, they are going to indicate the same quantity up to now in all the distribution. Right. So, now I expect you that you try to look into your books and try to take some simple data, and from there try to read that data and try to compute the probabilities. Once you can compute such probabilities, only say 10 observation or 20 observations, you will be more confident. And if you are not getting a data, I will say simply try to generate, say, 20 observations from a given geometric distribution and try to compute different types of probability that, for example, x less than 2, x greater than 2, probability that x is lying between 4 and 5, etc., etc. Now, the time has come where you have learned so many things, and I am sure that you should be very conversant in computing these things and understanding these things, and the ultimate is you have to match between the theory and the computation. That is the success of the data science. So, you try to practice it, and I will see you in the next lecture. Till then, goodbye.